Okay, we've already talked about Laplace, Helmholtz, and Poisson. We're going to talk about a related equation, the heat equation. And the heat equation has a rate of change of time of temperature is balanced by something that looks an awful lot like the Laplacian piece from all of those. So let's think a little bit about why it's called the heat equation. Well, this says if there's a localized anomaly, then I get some Laplacian on this side, and then there's going to be a rate of change in the same neighborhood. So in fact, what it says is that the localized anomalies in heat are going to spread out. You could generate anomalies in heat by varying your boundary conditions. Boundary conditions could actually vary in time in an equation that's a PDE with respect to time. And those signals would be propagating out into the interior. There wouldn't be a localized anomaly anywhere unless there was a time derivative to go with it. And in fact, in the long time, integrate after a long time, set an initial condition, set a boundary condition, and hold the boundary condition fixed and let it run out to infinity. Eventually we expect it to go steady, and the steadiness would say that there are no localized anomalies at that end point. So the localized anomalies are running away in the heat equation is one way to think of it. Okay, so let's try separation of variables on this and see where we get, just because that's our workhorse. So phi, this time I'm going to write it as a function of time times a function of both x and y. All right, let's plug in and see what happens. We know that we're going to sum these back up in the end. We're expecting to see kind of sinusoidal or exponential forms for this. Okay, plug it in. We get at this side of the equation, we get t prime x. And on this side of the equation, we get alpha squared x, Laplacian of x. Okay, times time. But the time actually isn't the time part is independent of the Laplacian, because the Laplacian only connects spatial directions to spatial directions. Because remember, the Laplacian is something special that has to do with tensors and things that are symmetric under rotations and reflections of the coordinate system. But all those rotations and reflections we're thinking of now are just in the spatial dimension, not having time as something separate. So we don't expect in this 3 dimensions or 2 dimensions plus 1 dimension of time separated for the spatial dimensions or spatial operators like Laplacian to know anything about time. So it makes sense that they're separated in the equation. If we were doing relativity, those pieces might be combined together because space and time are blended together when you're traveling very close to the speed of light. That's not what we're worried about. Okay, cool. We can bring that function of time right on out here, and now we divide through by xt, just like we always do on both sides. Divide through by the total solution we're examining, and on this side we get a t prime over t. On this side we get alpha squared Laplacian of x over x. All right. This side depends on x, but it's balanced by something that only depends on time. So both of them have to be constant in order for this to work. So let's set this equal to sigma and set it equal to sigma on this side. We can solve this equation, and we can solve this equation. Well, this just says t equals some constant e to the sigma t. It's just a growing or decaying mode. And we don't know whether sigma is positive or negative because we don't actually know much about what's going on yet. It could be positive, it could be negative. If it was positive, this would be growing in time. If it was negative, that would be decaying in time. Let's see what it looks like on this side of the equation. Well, it doesn't look like much yet, but let's rewrite it like this. Oops, I'm going to bring that over to the other side. Del squared x equals sigma over alpha squared. Sorry, terrible handwriting. Times x. And hey, let's move this. Make this a minus. But that equals 0. Look, hey, that's the Helmholtz equation, except in the place of k squared, we've got sigma over alpha squared playing a role. So we know we're going to get exponentials here for the x dependence of x and the y dependence of x. And so we'd expect to see something like, let's use a different coefficients, b plus e to the mx plus b minus e to the minus mx times c plus e to the minus nx plus c minus e to the minus n. Oops, that should have been a y. And y. That's going to be something that looks like a solution of this equation. And there's going to be a special relationship between m and n and sigma and alpha. And that's going to be where we find out whether sigma is growing or decaying. So we plug this into there and we find minus m squared minus n squared That's the derivatives, the x double derivative, the y double derivative of this operator, and then we have minus sigma over alpha squared equals 0, because each of those terms would be multiplied by the same x. And since we're not looking for a trivial solution of x, we're looking for a non-trivial solution of x, because we're looking for a non-trivial solution of the heat equation, we can divide through by x because it's not equal to 0. And we can clean this up by saying that we can make m squared and n squared both positive and make that go that way. So this, if alpha squared is positive as well, we have sigma. If this is positive, alpha squared is positive, sigma would be negative, and that would mean that we would be decaying in time for something that was exponential in both directions in space, or we could make this oscillatory, and we could be growing or decaying in time. But we know that in the long time solution, all of the localized anomalies, if those were oscillatory, would eventually have to die out to get to a steady state. That's where we go. One more quick thing to note, which is kind of a cute thing to think about. So if we just rewrite our xt that we had before, and I'm assuming now that sigma is going to be a positive, and so I bring along a negative sign with it, and then I actually assume that we've got exponentials in both forms in the x and y direction, because I'm thinking about localized, like, wrinkly things that are going to really upset this Laplacian. So I'm going with the exponential, with the complex exponential form. We could match, you know, this is just one of the solutions that we could have to this equation. We could actually sum a whole mess of these, and in fact, we're probably going to have to sum a whole mess of these in order to match the boundary conditions and the initial conditions. So we should really say that phi is equal to a sum over this kind of thing, with m and n being something that you could choose later. And hey, look, this is a Fourier transform in x, this is a Fourier transform in y. At t equals 0, this just becomes 1, and say that's the Fourier transform of the initial conditions. And then as time goes on, they're going to evolve. We have to sum over all the different m's and n's that we could in order to get the Fourier transform in both directions, but we could do that. Okay, so what happens in time? Well, let's plug this whole beast in there and find out what the conditions are, the relationship between sigma and m's and n's. On this side, we get minus sigma. On this side, we get alpha squared times minus m squared and plus minus n squared. Take the minuses out, and we get this equation. So this says the solution decays, all those wrinkly bits in the Fourier transform decay. How fast do they decay? Well, they decay as fast as m squared and n squared are large. The decay rate goes up and up and up when m squared and n squared get bigger. What does m squared and n squared mean? That means that we're looking at higher and higher, more and more wiggly Fourier transforms. So not only do the anomalies propagate in time, those are the things that are causing the time dependence, but the more wiggly it is, the higher the wave number, and the higher the spatial variability, the higher we're getting up in this sum, the faster it's decaying. So we expect all the little wrinkly things to decay very quickly, exponentially, but very quickly exponentially, and then the long, slow things would persist longer and longer. This isn't the whole solution, because not everything is going to decay with respect to time. We've still got another piece that we're going to have that would have these m's, one of the m's and n's, and being positive, so that we have an exponential, and then we have a variation, an oscillation on the other side. The exponential and the oscillation will cancel each other out, just the way that they did in the Laplace equation. And so in that case, that'll be the steady state solution that we're evolving down toward. And so in a sense, what we're doing here is not only summing over an m and n, but we're summing over real and imaginary m and n. And then the last piece to consider is that if I was at least imagining that phi would be a real number, of course, if we did this with complex coefficients here, we would probably have complex coefficients out front that would be setting different aspects of the phase in x and y of that crinkly field. So we might want to put a real part in here in order to take care of all that. The end.